All right, let's get started. It's the afternoon, pumped up, day 7, ready to go. I have a feeling I'll be a little bit slow on this one, but I'm ready for the challenge. So we'll see. Maybe I'll be fast. Day 7, no space left on device. Uh-oh. Seen that before. Not a good place to be. You can hear birds chirping and raindrops hitting leaves as the expedition proceeds. Occasionally, you can even hear much louder sounds in the distance. How big do the animals get out here anyway? The device the elves gave you has problems with more than just its communication system, which we solved. You try to run a system update in the middle of the woods. How does that make sense? System update, please. Pretty please with sugar on top. We've all ran that command before. Error. No space left on device. Perhaps you can delete some files to make space for the update. You browse around the file system to assess the situation and save the resulting terminal output, which is our puzzle input. For example, we cd to root, so that's the root node. We ls, which gives us a dir A with this information, dir B with nothing. We cd into A. Okay, so this shows us that, which is just like an ls command in Linux. If you run ls, you've got your directories and your files, but in this case, it also puts out the file size. So we know from an ls command that these 4 files exist in the directory under root. There's directory A, there's these files, and there's directory B. If we cd into A, we do an ls, there are no files in A, but there is a directory E, and, there is a directory E, and then there's a file F and G, and an h.lst file. I guess I don't know if the file names particularly matter, but if we cd into E and ls is ran, we get a file I, and then we're back up to directories. And we cd to D, and we run an ls, and then we get the output of directory D. So I think a couple things that are important. There is this operation of going up and down directories. The file system consists of a tree of files, plain data, and directories, which can contain other directories or files. The outermost directory is called /. You can navigate around the file system, moving into or out of directories and listing the content of the directory you're currently in. Within the terminal output, lines that begin with $sign are commands you executed, very much like modern computers. cd means change directory. This changes which directory is the current directory, but the specifics results depend on the argument. cdx moves in one level, looks in the current directory for the directory named X and makes it the current directory. cd moves out one level, finds the directory that contains the current directory, then makes that directory the current directory. cd switches the current directory to the outermost directory. Ls means list. It prints out all of the files and directories immediately contained by the current directory. 123 ABC means that the current directory contains a file named ABC with size 123. dir xyz means that the current directory contains a directory named xyz. Given the commands in the output in the example above, you can determine that the file system looks visually like this. Here are the 4 directories, A, B, which are in E, which is in A. These directories also contain the files of various sizes. Since the disk is full, the first step should probably be to find directories that are good candidates for deletion. To do this, you need to determine the size of each directory. The total size of a directory is the sum of the sizes of the files it contains, directly or indirectly. The total size of the directories above can be found by the following. The total size of directory E is 584 because it contains a single file. The directory A has a total size of 94853 because it contains files F, G, and H, plus file I indirectly. A contains E, which contains I. Directory D has a total size of this. As the outermost directory contains every file, its total size is this, the sum of the files, size of every file. To begin, find all the directories with a total size of at most 100,000, then calculate the sum of their total sizes. In this example above, these directories are A and E. The sum of their total sizes is this. As in this example, this procedure can count files more than once. Okay, so we need a couple of things. We need something to distinguish these as it's basically a tree system, and then you have 2 different types. You have file and nodes, and each one has a type of either a dir or file and nodes, file and directories. It's either a directory or it's a file, and then from there, if it's a directory, its size is based on everything that's contained within it. That's fair enough, but then there's this last little part that's complicated in the sense that we need to count A and E. So it's not good enough just to say, hey, what's the sum of A? If the sum of E is less than our 100,000, then we also need to know the size of E plus the size of A. Okay, so we're going to create a tree system, and as we're getting instructions of walking up and down and revealing more information, we're going to catalog that. My mind's going through some edge cases on how we're going to do this and some things we can run into. I'm hoping they don't put little traps in there like going to E twice under the same directory structure and then providing different output. But I think the way we can handle this is we can do like a dir size kind of function, and we can just pipe some stuff off to a channel if it goes over a certain value. And then we can kind of use a channel to handle that concurrency of like, I guess we could just walk every directory, and any dir that has a size, I guess we could pre-calc the size if we know it during our procedure and not recalculate it every time. Because I could see us where we do this one of two ways. I think the way that's probably the cleanest is that we create two different types of nodes and we create an interface on, and each one has a size, while the file type just has a size. The dir will have an internal size variable, and if the size is 0, then it will walk the structure and retrieve the size and set it. And that way, if it's called the second time, it's already there and cached. I think that makes the most amount of sense to me. So we need a couple of components. One component is putting this into a specific structure as we walk it, following the instructions, going up the tree and down the tree and building the nodes. So for instance, when we cd to root, well, we already know what root is. This will be an automatic instruction to go to a specific root node. And when we call ls, we know that that is the instruction for these next few lines until we get to the next $sign to record that under that node. So we know to create, because there's a dir a here, to create dir a. If it doesn't exist, create file with a size of, and then dir d if it doesn't exist. And from that node that we're on, which is still the root, this instruction is to go into the A node. So we will look for all the nodes with a given name. Let me look at the input real quick. Let me just see how crazy it is. It's not super crazy. Okay, I think we'll be fine. One of the things I was thinking of is like, how many directories will I have under a given directory listing? And depending on how many directories, you may not want to walk them all to like check their names. Let's iterate on that. Let's talk about the structure. I kind of want to do this in a structured way. I want to put it into a tree first, and then we can work on it. So like, what does that look like? So let's say we can have a type of file, and that has a name, which is a string, and a size, which is an int. And then we have a type of directory, which is a construct, and that has a name, which is a string, and that has a size, which is an int. And our directory, so then we also need one other thing, which is a type node, which is an interface. And this is going to have two functions, one called name, which is going to return a string, and one called size, which is going to return an int. And the reason we do that is because a directory is going to have a slice of node. And the reasoning for that is because now we can create these structures, and then we can have some sort of instruction to walk it, right? So you can imagine that a directory doesn't have a size, but it can have a size method that checks all of its items subsizes, right? And so you might have a structure that looks something like this. Something like that, right? Here, let's satisfy go here real quick. And because this is a interface, this has to be a pointer, right? Oh, sorry. Items, slice of node. Don't you like about this? I think it's because I don't have the methods yet. Does not implement node, missing method name. Yeah. Okay, so now we're going to create okay. And then for directory, the same thing. Let me just call this D. So nothing special here. Node not being used right now. Well, that's not entirely true. Unreachable code. Oh, there we go. All right, so this is what it's going to look like. So we can see here that now directory is not just size. What we're going to do is we're going to say if f.size not equals 0, f.size equals 2. Let's see how to do this. So for item and range items, this should be d dot. This should be d dot. Let me fix this. D dot size equals item dot size plus equal item dot size. So what this will do is when we call a directory the first time, if we don't have that directory size, we're going to go out and we're going to retrieve it. Now, my head's swimming a little bit because I do a lot of concurrent work. So if the size of the directory is not set based on our current iteration, then we're going to recalculate size. Now, the downside here is that if they throw in a trick where like they add another file or something to a directory, I have to sort of like devalidate the size. I could also do a technique where as we're adding nodes to a directory, we're calculating their size in advance. But the problem is with that mindset is that we don't necessarily know what's in the subdirectories until we ask. So what we're going to do is we're going to go through the entire instruction set and we're going to build our tree out first with our different nodes, and then we'll come through and we'll do some sizes. And as we walk that tree, we'll walk all the way down to all the directories and then all the way back up. We could do, there's one other thing I'm thinking about, which is we could do some typecasting on the interface, which is something that I think actually bodes pretty well here. We know what two types we're looking at. The other thing is we could add some sort of type indicator inside of file and directory, but I feel like the type is the right way to do that. The reason why is because I actually want to get a list of directories from time to time. So I know like, hey, if this is a directory, like I want to be able to walk each directory and get each directory size. And so I need to be able to know like what directories are there. A couple of things I want to just define out. So we've got our directory. This is what our structure is going to look like. And inside here, let's do one other thing. I might have a directory. And in that directory, I might have directory is going to have a name. Let's call it B. And it's going to have its own list of node, and we'll do a file. We'll call it WASI. Oops. Okay, so this is a pretty like decent test object. Okay, so this is kind of like an example of what we're looking at, and we want to make sure that as a size of a directory is traversed, we can get that size. And then we had talked about the caching that I'm going to do here. You know, the unfortunate thing is like if we were making files, these sizes could change, and then we'd we'd want to like figure out how we're going to devalidate the cache and make a decision. But I think this should be good enough. The one thing I want to do is, because we're going to have this thing where we're going to have to recursively go down and get all of our directories, I want to create a directories method on the directory. So like we can definitely do the size, but if we want this to return a list of nodes, and these are just specifically the directories. And the reason we're going to do that is because when we start at the root node, there's this extra rule in here that says that we want to count directories twice. So we're going to have to count the A, but also the E, which is a subdirectory, because it meets that same criteria of being less than 100,000. So then we got to sum them together. So we got to sum the 95437 and the 584. So we're going to have to create a method that kind of loops through that and gets all of those sizes. And so I want to be able to just say, hey, give me the directories that I have. And I don't think the structure that we have right now is going to really be a problem for that. So we want to do switch. Okay, so it's going to be for item in our equal range of d dot items So we're going to just loop through this, and forgot the colon here. And we're going to say switch item something like that. And then what is it? T equal, okay, just case. Okay. So we could do case, and we're going to directory case file. We don't really have anything for a case of file, so we're not going to really do anything with that. So I'm just going to delete that for now. And we're going to return this as that type. So I'll use this reference here. So I think we can do actually we can just directories equal append directories item. Okay, so now we've got our return directories. Okay, so if it is case type directory, go ahead and add it, and then maybe we could have this return directories and files separately as two separate lists, maybe, but I'm just going to leave it as this for now. So we'll get all of our directory nodes back. And so that should, in theory, given this set of instructions, I should get back this directory with the name of B. So we're going to use this for our test, and we're going to see first, before we implement all this instruction on how to build the tree, if our underlying pinnings work. So our input is going to be a directory, and we've got this as our input. So we'll copy that, put that here, boom. And then we'll get rid of this like that. And our function we can do input dot size, right? Test dot input dot size. And that should be 0, 1, 2, 3, 4, 1, 2, 3, 4 plus 1, 5, 8, 9, 2, 8, 2, 3. So that should be 2, 8, 2, 3, 2, 8, 2, 3. Okay, let's run that. Expected 2823, actual 0. Okay, cool. So we got something to iterate on here. So, oh, yeah. Simple fix. Okay, perfect. So now we know that if we walk a directory from the top, we get a size. And then we're just going to iterate on this a little bit more. So what I want to do is test the second directory. And we could restructure this. This is kind of a poor man's way of doing it. I'm just going to go with it and say that we want to test directories sub 1 or 0 because we want to get the directories of root, which is going to give me, oh, the answer for that is actually going to be 1, 2, 3, 4. We just want to see if that works. From a directory, do I get that? Expected 1, 2, 3, 4. Oh, because I didn't run size. Okay. Actually got 1, 5, 8, 9. Oh, that's right. That's because this is a file. So, okay, so now we know that our structure kind of works. It's walking it down. And now we just need to learn how to move within this structure. So there is something that I think we're missing still, which is a pointer to the parent. And the reason why I want that is because I want to be able to walk back up the directory. And we can do that two different ways. We can just have a reference to where we are in the structure. Suppose that's fine. The stack, so to speak, where we're walking. Or we can define the parent node on every child, which can get complicated when you're moving nodes around a tree. But I do feel like that's going to give us the most efficient way to move up and down the structure. So the way we would do that is you would have a parent, which is a node, and that would be on both the node and the file. And then because we're using this interface, we want to create a method to access that, which is just simply parents, and that returns a node. Okay, so that gives us the ability to walk up, and then we know kind of what the children are. I guess really instead of calling this items, we can call them children, and maybe that would be a better way to express this. I'm actually going to go ahead and make that change here. Children. And then we know like where we're going up or down between. So we did add a parent method, and so we do need to just do this here. And we'll do that on file as well. So I may, if I was to structure this differently, I would have these in different files, but here I am. Maybe we'll make some of this cleaner later. Okay, so we're going to run this test. As soon as I can. Oh, what's going on? Test function at cursor. Okay. So basic functionality is still there. We're not going to get super more complex here. What we're going to do now is talk about how, with a given set of input, we're going to walk this structure. So I'm going to create a new file. I'm going to call it day7-test.txt. That's going to be our test input. And if we go back to admin of code here, we know that we've got some test input here, and we can iterate on this. So now we got to work on our functionality that walks this line by line and makes moves. So we're going to, in our bad habit, AOC method, we're going to get a set of data, and we need to split that data based on a separator. And we'll call that lines. And so each line is going to have an action. So if lines sub 0 equals $, we know that we're taking action. And there's really and we know that we need a root node. So we're going to call this root, which is a directory with a name of / and a size of 0 and a parent of nil. Okay, so we don't have to define this actually. So we'll leave it at that. We really don't need to define that because the default 0. And so through each line, we can just simply say, there's not a whole lot of actions here. So if we see that it's CD for line range lines, if our line is this / right, we are going to so our current node is going to be root. So then we're going to do current equals root. So that'll put us back to current each time. Okay, done. Let's define a couple of other actions. ls. We'll switch this to a switch statement. We might not need this continue, but I'm going to leave it in here for right now. Let's take care of all the CD actions because I think those will be pretty straightforward. If we ... it's going to be current dot parent. Current is root. Root is directory var root node. Okay, So now that should be fine. Current.parent. Boom. Okay. So now we know that if we're going up a directory, then that is that. And okay, so things get a little bit more complicated there. Maybe the case statement isn't the best option here. If line sub. So we could either use a regex here, or we could just say, hey, if at this point, if the line is, we'll have to implement ls if we want to avoid an issue, but we can say low dot contains, really it's strings dot contains. Our string is line and our substring is that. So if that's true, then we know we're going from current into a directory. So you know what? I think actually, let's go back to this because I think we can. Parent is always going to be a directory. So I think we can fix this. But it needs to be a pointer. The interface needs to be that. Okay, so directories. All right, so current is current. So current.directories, sub dirs. If sub dot name equal to see 1 2 0 1 2 3 4. We're going to do a replace line, and we're just going to remove this chunk. We're going to replace it with empty. So if the name, which is a string, replace just once. If they're equal, then current becomes sub. There we go. Is this testable? Just real quick, if I run this, is everything still working? That was really slow. All right, let's just keep going. All right, so if we get a match, we continue. I will say, like, if we're in this function and we don't get anything returned, you messed up. We probably did something wrong. The value of current is never used. Ah. Well, boys, got a little bit of a problem here. So we reset this, but we don't want to just continue up one. We did this label thing, right? Where do we do that? Was it day 3? Yeah. Go to main. Yeah, that's what we want to do. But if I do that, then I gotta actually change the variable. So I want to break out of this loop. I don't want to continue this loop. I just want to break some done. Problem is, we'll just do that. I could do the whole go to, but then I have to change the whole iteration. What'll happen is if I do a go to main here and I use this for range iterator, the lines thing will get reset every time, and I don't want that. So I'd have to maintain like a for I in, maintain the index, and then set the index initially, and then manipulate the index as I go. Don't really want to deal with that mess, so this is the way we're going to get around that. So we're going to go ahead and just replace that, get the value, iterate through them. One thing I'm going to do is I'm going to create a dir name outside of here just because we don't need to reprocess that every time. And so that's where we're going. Okay, awesome. So let's take another look at our input. So what I'm going to do is kind of take an advantage here, and I'm just going to ignore the ls command. And if there's not a $sign at the beginning of our line, then that's input, right? So it doesn't matter what node I'm in when the ls occurs, because that's going to either be the last thing that's displayed. It's possible with the input, because they do like to add little tricks in here, that there is somewhere in here that puts data out after a CD that's kind of buggy. We're not going to worry about that right now. I don't think it's a problem. So I'm just going to kind of code for what I know. And that is, if it's $ls, ignore it. And then we can do something where if the first character is not a $sign. So switch case $sign, was it ls? Do nothing, essentially. So we're just going to continue. Okay, cool. So now all of these things can happen. And if it's none of these conditions, right? So what we can do is if lines sub 0 equals a $sign, logros.fatal. Fatal is going to crash the program or end it. And so we're just going to like say, hey, found operation with no access taken. You messed up. No directory exists with name $s. We're going to call this dir name, and then we're going to do fatal F here. So again, these are two conditions where if, so now we've got all this stuff structured. We need to read in the data, right? So if this is just kind of like our out, this should be line, right? Oh, did I not put that in that block? Okay. This needs to come out of here and go here. We'll make that a run, that's fine. So this is just kind of a fallback, like, hey, I messed up. Something I did above is not right. So now, if line 0 to 3 equals dir, right? Is it dir? dir lowercase. Okay, so if it's equal dir, then we're going to, so that's 3 places. We learned this from our last video. So we're going to then say current dot children equal to append current dot children. Boom. Directory parent equals current. Oops. Okay. Name equals index 5 to the end. Is that right? I think so. And then size is 0. Children is not set. Oh, we may want to do that actually. So in our root, we do have children, right? Because we decided to do that. And we probably should just initialize it. It's not important. Well, it's important because we would, if it doesn't exist, then we can't append and we'd have to do a nil check. Probably better for us to do a nil check. Yeah, you know what? I could do an add function. I'm really splicing things here, but we could just say if current dot children equal nil equal what, slice node empty, because we know we're going to append one. That way the rest of them are all just represented as node, and then we don't have to do it here, and then that will continue on. Okay, so now we've got whatever it is, whatever the name is, several characters, 1 character. We saw from our test input that it's several characters. We're able to do that. So then if it's not dir, right, then what is our other input example? Our other input example is some set of digit with some file name, which really doesn't matter to me, but it looks like it's just split by space. So then the next option is simply, and we're going to continue this, right? We're going to keep continuing because we can break out early. You know, we don't need to follow any other paths. It just makes our code a little bit cleaner. Our default case is file then, right? So here we go again with, I suppose I can move this 1 step higher and not do this twice. We know we're either going to add a dir or file. I'm not going to do an else. I don't like else's. If I can exit early, I will. I just, this is my preferred way. I think it's easier logically to think, hey, if we meet this condition, we do this thing and we continue on to the next iteration. So that's what we're doing. So then really the answer becomes, well, it's a file with a size. So parent is still current. This is a file now. And the name becomes, okay, so we're going to do a strings dot split, and we're going to split the line on a space. So S sub 0 is our size, and S sub 1 is our name. S sub 0 is our size, but this is a string str convert A to I to A. Nope. This one. And don't care about that. Size is size. Okay. And I think that will do it. So if I did everything correct, we now should have some sort of input, right? And we can start at the root and traverse it. And so what we're going to do is we're going to do a total 0. So I want to do something where we can call recursively the directories, because really it's just a recursive function. So where we go all the way down and func get directories under size, and our size is some int, and our input is a directory, right? And our return is some slice of directory. And so what I can do is say if d dot children equal nil, return, we'll do dirs d dot directories if dirs equal nil, or length of dirs equals 0, because I feel like that's more likely what's going to do. Then we return nil. All right, so if this is true, that, and if it's not, then what we're going to do is for, this is what we're going to do here, it's going to be iterative, for d in range of dirs. Okay, so now we got this thing going on. We're going to say d equals to append under get dirs under size, and we're going to pass in the d and the s, and we're going to say if under not equal nil, append it's fine, u equals to u under, boom. Okay, so return u. Okay, so what we're going to do is we're going to recursively call this function from the top all the way down, and what we should propagate up is everything that is under a certain size. So we are simply going to do for and what Okay, we'll omit the nil check. Thank you. Thank you, Go and VS Code, for making me a better developer. All right, so go into our day 7 test and test AOC, and we're in t.assert, dot equal t, our expected value. What's our expected from the input? The expected is 95,437, 95,437. Our input is AOC, and then we gotta do that. I think that's it. So was it day 5 we did the file testing? Let's see here. Yeah, we'll read this. Day 7, boom. And we'll do assert.noError. And then string B. We got to pass the test here. All right, boom, go. Actual is 0. Okay. Well, it turns out, guys, that you actually have to return the total if you want to test that value. Get rid of this. Okay, my split function's broken. What did I do wrong? I've done this like 6 times. Is it because it's not that it's interpreted as this? Is that the problem? Fatal, you messed up. No directory exists with name A. Okay. Well, no directory exists with name A. Okay, so let's look at my test input, which is here. dir A. DIRA. That's because I'm trying to CD to it. So, all right. Huh. Well, it's not going to. Yeah, okay. Oh, wait a second. There we go. I think that's it right there. We'll just debug it real quick. Yep. Okay. It panicked. Right. Okay, well, I think that's because I've got an extra line at the end of my input. Let's just try it without it. Well, didn't panic. It didn't panic, but I still have a 0 size. So why? Okay, well, we will start here. Get directories under size. Directories. Length of dir, return unknown. Otherwise, under each dir, let's try it out. Okay. We're popping. So I need to return self. All right, I got to finish up here. But I think the issue was that we weren't returning anything if we weren't checking size. So, duh, it's not going to work. Missing return. We need to append to you. Oh, because I'm an idiot. Sheesh, Chris, we are not doing great today. Aha, 94853 versus 95437. Okay, let's check one other thing here. So let's make sure that in our test we're passing in the right value. The expectation total size is 95437. That is 94853 plus 584. At most 100,000. So it's a less than or equal to problem, that's for sure. Dir under value. Where did I put that function? It is at most the size has to be less than or equal to our limiter. I don't think that's the issue though. Is it? 94853, 95437. Let's look at this again. Oh, wait a second. 94853 is the upper value. So it's not including the total from both directories. So why is that? So we know that if the current directory's size, we're getting there. We're getting close, boys. Okay. There's something wrong with my recursion here where anything under is going to get added. So let's look at, we're going to pass in root and it's going to go and say, hey, what directories do you have? Okay. And then for each of those directories, pass in, I'm going to change this to sub and sub. I don't think that'll change the behavior, but it just, okay, we're getting close. We're equal to append D. So we're going to append ourselves. If we're less than the size, we're going to append ourselves to U. And then we're going to do that for each directory under size. All right, we're going to do one last debug here. So close, guys. So close. Okay, so there's two problems that could be occurring here, which is one, my structure is not great. So if we look at D, D has children. Is one of these children? Yes, it is. It's a child of E, 584. So when, oh, Ah, I see. I see what's happening. Okay, mistake. We're assuming that in this case, we're saying, hey, if there is no other subdirectories, just don't move any forward. And the E is the bottom node. There are no leaves from that. So we actually want to do this append earlier. So we do want to always put U in here. We want to move this up. So that's always up here. And we don't need to, we actually don't need to do this at all because the range on the DIRs isn't going to produce anything. So I'm just going to take that out, bad practice, and this should pass. Cool. Now we're rocking. Okay, so let's go ahead and AOC string part 1, day7 text. We'll go ahead and create a new file, day7-1.txt. And in here, we'll get our puzzle input. We'll see. Seems pretty high. That's done. Please like and subscribe, and I'll see you next time.